So remember we did gas phase, reactions, where you figured out what the extent of reaction was. Unfortunately, because of the way I very stupidly split that between test 2 and test 3, I still have it on test 3. It's, I can't not test on this, and I didn't want to put it on the final. I may still put it on the final. I said I don't want to, I didn't say I did. So, so yeah, I do have something on the final about this, and just recall that what happens is, big picture is we have the Hess's Law. Now Hess's Law I do not have on the test because, I mean, it's a high school level thing, but regardless, remember that this guy is the sum of products, you know, the chemical, the stoichiometric coefficient. Remember this is not formation, but this is not fusion, it's formation. So you've got your Hess's Law, sum of products minus sum of reactants. Okay, and stoichiometric coefficient, and number in the table in the back of the book. Sorry, I'm thinking and talking at the same time doesn't work sometimes. Okay, so again, Hess's Law, high school stuff is not on this test, but it gives you this for a reaction. And of course, I've chosen a very simple one. And the point was that in high school, you learned if that's negative, you learned it was spontaneous. But the issue here is now remembering that these are actually chemical potentials. And remember what makes a reaction go. Reactants have chemical potentials that are too high compared to what? Everything's in comparison compared to the products. So the reactants form products. And that will happen until the chemical potential of the reactants drops, the chemical potential of the products rise until they equal, then the reaction stops. So the way that we adjusted this is to take into account, since these are gases, we haven't done liquids, and we're not going to do chemicals reacting in solution, which is just due to activities. I'll actually write that down in a second anyway. Okay, knowing that it's a matter of getting chemical potentials of products minus reactants. You have to let them change as the reaction occurs. Well, why do they change? They change because the partial pressures are changing, and delta G per mole, which is the chemical potential, is sensitive to the partial pressures. So what I want to remind you, and I almost screwed up, even though it's in my notes, is that the equilibrium constant for a gas phase reaction is a natural log full of partial pressures. Right. Again, don't forget this. Changing partial pressures as a reaction occurs is what changes the chemical potential, and they'll keep doing that until the chemical potentials of reactants and products are equal. That's when it stops. So that's the big picture. Okay. And this, of course, is equal to the actual reaction, because remember, one of the issues is that the number in the table in the back of the book are for pure substances, which is automatically blown in the case of a reaction because things mix. And they're also done at 1 bar. And these are, again, part of the point of this is that you're not at 1 bar. As you know, the partial pressure of reactants hopefully is going to 0. Okay, so table changes the partial pressure equals the actual thing, but when you're at equilibrium, this will be 0. And therefore, looks like I'm going to use the board weird from now on. And let me do an example to be more concrete. Take what happens if you blow up a balloon, you get hydrogen radicals that go on to form H2. Again, we're doing these in the gas phase. And tell you what, let's make it generic because who knows what I'm going to put on the test. Let's make it 2A goes to B. And what can I ask you? Well, I could probably, it was torture to build these equilibrium constants and to work with them. And so I wouldn't make you do all that without putting it on the test because I'm hoping you can handle it quite well. Makes it easier for me to grade, gives you a good grade, everyone's happy. Okay, so the way I would do this, and again, I'm going to put this in generic form. I just wanted you to, this is real, okay? I felt like maybe I did this a little too much. Okay, so, this is 0, so I'm just going to put minus delta G. And if you need this because this isn't a Hess's Law deal. This isn't a Hess, that was technically last exam. I don't think I put that on the last exam. It's natural log of K, and so all of this is about building up K. Now you may recall that to build K, you have to get the partial pressures, as I've been babbling on for quite some time now. You have to get the partial pressures, and then you got to remember that the partial pressures are actually functions of mole fraction. It kind of sounds like I'm getting towards Reynolds' law. I'm not, because this is a gas phase reaction. And remember, this all came before Reynolds' law. Regardless, the partial pressure is a function of the total pressure times the mole fraction. The mole fraction, what you do is you're going to figure out how to turn that into the extent of reaction, and maybe you don't solve for that. Okay, now if I ask you to do that, to build K as a function of the extent of reaction, that thing I always called alpha, I would give you the table so that you don't completely blow this. I found in the past, because this is obviously a standard type of question I can ask. I have a couple of ways of doing this. I could ask you to build the table. I could ask you to solve the table. You saw all that on your homework. If I asked you to create K, given all the stuff I'd say, I would give you the table and remind you that you want to figure out the number of moles at the start. And of course, you don't have products, so put a 0. And no matter how you do the reactants, you're going to get the right answer. So let me do something a little odd. I'm just going to call it N. Now, that's a little odd because you might want to go with 2N. Oh, let me see what I did in my note. Tell you what, actually, let's do that, because I do it in my notes. I don't want to screw this up. I call it 2N. It doesn't matter. If you started with N, you're just going to end up with half an N at the end. If you start with 2N, you end up with 1N at the end. Your answers will still be correct. That's the thing that's amazing about this, and that's because, remember, these are ratios. That's why. Okay, anyway, I'm babbling. All right, now what I do like about this is that it's a bit of a puzzle. I now want you to figure out what are the moles during the reaction. And the way you think about this is you think, well, what would I have gotten at the end? And let's see. If this reaction goes to completion, so that means I have a little alpha. Remember, alpha goes from 0 to 1. So you've seen this. That goes from 0 to 1. And if I know that it's 1, the reaction has gone to completion, and that means I better have n moles of product. Okay, so this start thing, you don't even need it, by the way. I want you to write it down so that you don't screw up the finish. That's the part that matters. Okay, now I've got to just think about what do I do with this. Okay, I've got to end with 1 mole. Again, if the reaction goes to completion, I've got 0. What am I saying? No, I've got 0 moles. Right, so that'd be 2n alpha. Okay, that goes to 0, right? Okay, so again, it's all in my head. I just make sure that it works. And then the next thing I need to do is figure out the mole fractions. All right, now that's where, again, remember this is just kind of a little formula. Mole fractions are number of moles, and I define that divided by the total. So now you've got to figure out what the total is. And let's see, so the total is 2n minus 2n alpha plus n alpha, which is 2m minus alpha n. Be careful about, I'm going to try to be careful. My alphas do look like 2s, I'm aware of that, so be a little careful, I'll be careful. Okay, so again, if the extent of reaction is 0, I've got 2 moles, which I just decided to do that. And if the reaction goes to completion, I have 1 mole, which, yes, that's right. Okay, so now I build up the mole fractions. And to remind you, I told you that some of you who come by office hours, which is very few of you, that one way you know you've done this correctly is when you can factor the n out. And again, be really careful with those alphas and 2s. You should be able to factor the n out, and your final answer does not have an n in it. Again, be careful with that alpha. Did I do that right? Yeah.
Should be 1 minus alpha.
Wait, well, what?
Shouldn't it be 1 minus alpha?
Huh?
For the A? I mean, for the top one? And you might factor out the 2?
No, I don't
Factor
know.
out a 2 from the top?
Why would I?
Oh, I see.
Right, it's fine. So, yeah, I could, but there's no point. It would just kind of come.
I thought they're all lights, man.
Oh, that's fine, it's fine.
And alpha looks like a 2.
Oh, that's what, oh, yeah.
On the bottom of the dark.
Yeah. Sorry about that. I see, okay, I see what you did. Yeah, just be careful with that. I'm trying to be careful. It's just making my weird alphas. I'll try to write them a little exaggerated. Okay, and then I'll draw them like super flat. So, because I get confused myself. Okay. All right, now that you've done that, you can see that this would probably be a derivation question because it does take a bit of time, and the derivation questions are big time, which means big time. ln k is natural log of chi. What am I doing? I'm doing. Sorry. Let me. What am I doing? I'm jumping ahead. My bad. I'm going to say that A is proportional to the mole fraction of A times the pressure, and B, that's the product, is equal to the mole fraction of B times the total pressure. Because you can imagine, I could also ask what's the effective pressure. I'm going to remind you of that in a second. And I'll tell you what, let me give myself some room here. I'll just keep working down. I can see I'm just trying to make myself into a hole. So I'm going to keep working down. And, okay, so, and I'll just start, I'll just write the whole thing over again so that you don't get lost with what I'm doing. Okay, so natural log. Okay, so this ends up being a pretty big matrix. So now, again, one of the few things you do got to remember, actually, what did I say? A few things. Remember, I did actually write this test with my mantra of this is a bit more memorization based than normal, which I don't like, but it's what it is. You do got to remember products over reactants. Okay, partial pressure of products over reactants. That means that I've got the mole fraction of the partial pressure of B. Remember, it's divided by the initial. So remembering that all of this comes about from the change in chemical potential via pressure. You've got your final pressure, your initial pressure. And because the stoichiometric coefficient of the reactants is negative, you flip those suckers. So A is now reversed. And reversed in the fraction sense is 1 over. Okay, so that's chi A times the total pressure, and this sucker is squared. Okay, now I insert the above alphas, and so I've got alpha over 2 minus alpha. Sorry, I want to exaggerate that again because that's too much. OCD, I'm going to explode. Okay, there we go. I think that's reasonable. Okay, then I've got the other guy, 2 minus alpha, 2 minus 2 alpha squared. Now remember, that's A flipped over. And I've got to remember my effective pressures. I'm going to have PO on top and the total pressure on bottom. Now that you might need to know is if I ask the effective pressure. Okay. Now actually, if I was to go this route, I would actually stop here because to solve this, I would have to give you a delta G, you take the exponential for it, and then you solve for alpha. I could do that if I maybe set up a simpler and A goes to B, then it's solvable. It would be solvable, but in this case, it really wouldn't be unless we had the program. Sorry, question up there?
Can you explain again why the XA is split?
Is a reactant. So now this was a while ago. This was actually right before test 2. Remember, again, I'm sorry, I did split this section in two. It was because the, it was when you did, when you looked at the difference in chemical potentials, which is of course everything, the products were higher than the reactants. Reactants were higher than the products, sorry. Reactants are higher than products. You had to scale the chemical potential by the molarity, right? 2A, so that's the 2. Now, hold on. Remember that the 2 is actually a negative because the A is going away. Right, and so because of that negative sign, propagate a couple of steps. I can't show it. I did do it in class. You're going to end up with the natural log with a minus sign in front of it, which ultimately flips the innards. That was like 6 weeks ago that I showed you that. So it's good that it came up, but and hopefully that'll help you remember. But yeah, that's ultimately why the innards of the reactants are flipped, the products are fine, because those are forming, the other one's going away. Okay, so again, I would just, if I did this, I would trust that you could then solve for alpha as you did on your homework. The other thing I could do is ask if pressure increased, what would happen? Now, the way to do that, if I ask that, for one, I might ask you to come up with an equation for pressure. And again, I kind of like that because it makes you come up with phenomenological, this would technically be a phenomenological model that's very easy. Of course, you would start at 1 bar. Oh God, what am I doing? 1 bar. Because pressures are in bar. And let's see, you have to, now I have to just look at that, 2A goes to B. I just have to figure this out. And so I appreciate this, it's clever, right? There's no formula for this because if you're, look, I could train a cat to solve a formula if I had enough time, but that doesn't mean the cat understands it. So you actually have to look at this and understand that, given that our initial pressure is 1 bar, remember, I have to do that because the number in the table in the back of the book are at 1 bar. I need to start at 1 bar no matter how many moles I have, and I'm going to shave off. I'm going to shave off pressure. Now that actually goes to 0 pressure, which is not right. It actually should go to a half. So there you go. All right, so that's how I can define pressure. So I could ask you to do that for whatever reaction I do, and I, by the way, would not do this one because that's too trivial. I like that. What else could I do? I could also say, which way does the reaction shift? Well, I would want you to look at this and figure it out. But before I do that, I like this question because you should be able to look at the equation and get the right answer, and knowing that, explain it accurately, right? I look at this, I know that if I increase the pressure, Le Chatelier's principle says it wants to relieve the pressure, clearly I get more B. Right, so that's easy. So if pressure goes up, you get more B. And therefore, alpha is higher. Sorry for all my shorthand. Okay, so again, you can look at the reactions and know what happens, and you could have done that in high school. Now, of course, this is college, so what I want you to do is do a slightly better job. Let me write this, and then I'm going to toss the board up so you can see it. I know you can't see it right now. I'm going to I'm just slightly simplifying this, and so I want to try to figure this out. Okay, so this is K. Notice I got rid of P0 because it's just 1 bar. Okay, if this goes up, then this has to go down, right? Now what I'm really testing there is, do you remember that K is pressure? I'll write that down. K is pressure dependent. And remember the thing when I first introduced that concept, and I did explain why it doesn't bear repeating, what was kind of cool about that is that you say, oh, okay, well, pressurizing doesn't do anything, yet we've already established that you'll get more B because that will fight the change. That's Le Chatelier's principle. Okay, just because K is pressure independent, it actually means that some things do change. They change to keep K pressure independent, right? Okay, so having solved the correct K, and seeing that pressure's on the bottom, you see that this sucker has to go, wait, what have I done? Sorry, my bad. This is 1 over something that goes up, so all of this has to go up. This is 1 over. Fractions, they kill you, right? Okay, so all of this has to rise, my bad. Now, don't forget, you already know the answer, right? Test taking strategy, you know the answer is alpha is bigger. Now you just got to figure out why, all right? I'm looking on top, and I see if alpha gets bigger, this isn't helpful, because, okay, it's helpful here, but it hurts there. This makes it bigger, but this kind of fights that. So this doesn't look helpful. Let's look at the bottom. If alpha gets bigger, this gets smaller, and 1 over a smaller number is a bigger number. There we go. Okay, therefore, alpha gets bigger. Okay, again, see what I've done? I've asked you to, at a college level, figure out how to use that equation on top. You've included pressure. You have a phenomenological model for pressure, which is really quite accurate. And then you can also answer me which way do reactions shift with pressure using your high school freshman chemistry knowledge. But letting that guide you at a college, senior college level, looking at something that's actually kind of complicated, but being able to figure it out. There you go. All right, so any questions? That's really about all I could possibly ask, other than potentially give you this and have you solve alpha, but clearly that does require a computer unless I come up with something very simple. We're okay. I've gone over this a little bit more than I meant to, but I knew that this would probably be the least on your mind. The next thing we hit was electrochem. And I've already told you what I was going to do, and I did do it. But let me remind you of how this works, because I did see on some of you on the electrochem homework, I did go through these. To some, I don't look at all of them, obviously I don't have time, but I did go through some of them, and I did see what some of you, I look at the mistakes, right? I don't need to look at the right answers, I looked at the mistakes. And I just want you to recall, again, memorizing. God, I hate that, but whatever. If it gets high grades, then that's great. Remembering how I want you to do this, because the way I'm showing you to do this is how nature works. Although there is a cheating way to do this, but that, just like I just showed you, it's fine to be guided by little cheats, but those are not answers, right? That's what I'm really trying to get across. Okay, when it comes to electrochem, which again, I'm doing this in a biochem class because of batteries, right? Batteries are important. Remember that you're really summing delta G's via the EMFs. Remember EMFs? I'll write down the formula here in a second. This is via the Nernst equation. Here I'll write that down, which is the EMF is this, of course, our favorite minus reaction G. This is the number of electrons in Faraday's constant, which never bothered us. Remember, Faraday's constant, it's obviously important, but it never really bothered us. Also recall that, crazily enough, so this is just a giant Hess's law. Hess's law is all about delta G's, but I can relate delta G to voltage via the Nernst equation. And the other thing is that our reference state are no longer forming the things in the battery from their elements. Instead, we have the standard hydrogen electrode. And remember those, that notation I use, my ox is red. Remember that, okay? And everything's measured via comparison to the standard hydrogen electrode. That is the elements in their standard state equivalent. And okay, so that's just the background. Now, what am I going to do? This is an example of what I'm not going to do, but is a very difficult question. And then I'm going to remind you what I said I'm going to do. Okay, so I'm going to give you the things that you find on Google. Let's do I gave myself a really difficult one. Now again, I'm not going to do a question like this on the test, and we've already written it. Oh, I didn't space myself well. And remember that these are in volts. That's actually not that important. You look on Google for the numbers in the table in the back of the book are reduction potentials. And this is a very unusual one. What I like about this is that I always would just assume that something with 2 electrons would have a greater voltage, and that's actually completely wrong. Why would it be? Okay, so I've given myself actually a really hard one here. And the reason is because this is something I screwed up in class, and that's why I'm doing it. My gut tells me, I think I might have even said this before I corrected myself on that extra Friday. Okay, to convert this to delta G's, we're going to take the voltage, multiply it by minus the number of electrons, and so this ends up being minus 0.68 minus 0.52. Okay, there's a couple of good things about this. One is that I'm not going to reverse them. Remember, if I have a negative voltage, reverse it don't even think about it, just reverse it. Because negative voltages mean positive delta G's. That's not fair, right? That's tying a chicken around Usain Bolt's leg and expecting him to run as fast, right? No. Delta G's need to be negative, or remember, we're trying to figure out how this reaction goes. You don't want to consider something that you know doesn't go to begin with. Okay, I've avoided that problem because of what I gave you. The delta G's are negative. Now I need to figure out what the right reaction is and what the voltage is. Okay, now this is what I screwed up in class because my gut instinct says to go here, right? Now, flash forward, let me give you the summary. I'm going to prove that I've done this wrong. I've just made a mistake, right? Now remember, I got twisted up really badly in class at Extra Friday when I was doing this. That's why I've intentionally given myself a hard problem. What I should recognize is that it has to be this one. Okay, I'm cheating now. I recognize the answer has to be this one because it's the biggest positive. But I figured out my delta G's, and that's the biggest negative. It's ultimately wrong because chemical potentials, remember these are chemical potentials, they are in charge, not the absolute G's. That's why this one's going to win. Let me intentionally screw up. Let me be guided by the delta G, not the chemical potential. That's wrong. That's why I'm about to make a mistake. But let's say this is the winner and this is the loser. Okay, so now what I do is I have to conform the wrong loser to my wrong winner, so I'll do that. The problem is that the electrons can't be on the same side, so I'm going to have to, I'll wipe this out. I'm going to wipe this out, and I'm going to reverse this one, having established that I think it's the loser, which again is wrong. You know what, and I need to put a 2. I need to put a 2 because, again, I've got to wipe out the electrons. Remember, this is a Hess's law. Actually, I'm sorry, I think I forgot to mention that. As you put these together, remember, your job is to wipe out the electrons. Because remember, if you don't, then that means charge is building up. That doesn't work. Okay, and so what do I get? I get so minus 0.52, which is then plus 1.04. Okay. Okay, so then I can write down the net reaction. These cancel, I could write that out, and then I could also figure out the total delta G, and I get 0.36. Okay. Is that right? Well, I mean, I've added them correctly, so that's right, but no, the answer is wrong. Delta G is positive. I just put a ball by a base of a hill and it just shot up the hill. No, balls don't do that, neither does electrical chemical reactions run in reverse, not on their own. You actually can, what you can do is you can actually take like a 9-volt battery and connect it in reverse to a 10-volt battery, and you can actually do stuff like that. The batteries, by the way, will explode if you do that. But so this is me doing it wrong. Okay. Recognizing I've done it wrong, I now realize that this is the winner, not that one. Oh, and look at that, it does have the right chemical potential. So let me start over doing it correctly. And I'll explain how this is analogous to the actual one. Okay, knowing that this one is correct, and I'll make sure I did it. Okay, I'm still going to scale it. I still need to scale it. I still need to get rid of the electrons. And by the way, it doesn't matter which one you scale. It just matters that you figure out which one is right. I'll just label them this way. Sorry, I'm kind of rushing at this point. Now remember that the chemical potential doesn't change, and that's the voltage doesn't change. So you see why this is going to win, because it's the big negative. Now I got to get the other guy to flip it. 2 electrons. Okay, so now my electrons are gone. And now, of course, part A is to write down the net. Okay, the electrons are killed off. I've got, oh, I'm missing a 2 here, aren't I? I have 2 coppers on the left and 1 on the right. That's not right. Okay, so what I end up with is 1 copper solid. So this is an electroplating reaction plus, okay, not a big deal. Oh, wait a minute. I do got to, remember the number doesn't change, but the sign does. This is a plus 0.68 for a total of minus 0.36. And then the voltage is now this delta G, oh, minus sign, remember Ben Franklin. And I guess, I don't remember if that's multiple. I forgot what the Faradays do. Divided by the number of electrons. This is a 2 electron, so this ends up being 0.18 volts. Okay. All right, now, is that consistent with the cheating method? Again, now you do this, it's no points, but this is the dominant one, and that one has to get flipped because they're both reduction potentials. This minus that, oddly enough, 0.18. Right? That's again how you know how you did it right. Now, as I mentioned, this is a really hard, this is actually the hardest thing I could come up with. So I did not do this on the test. Instead, what I've done is a question, as I mentioned before, but it bears repeating, that I've always kind of been fascinated when I look at the tables of reduction potentials, how many times I see that there's multiple possibilities. So what I've done on the test is I have 2 cells. I remember that there's a left cell and a right cell. And don't forget, remember salt bridges, why you need a salt bridge. That's on there, by the way. So cell 1 has 2 possibilities. Okay, and then cell number 2, I just give you 1 possibility. So just assume that, yeah, you can't mess with it. I'm only giving you 1. And what I'm asking you to do is, what's the net chemical reaction and what's the net voltage? Now, hopefully you see how the lesson here, the reason I chose this one is because, excuse me, it was very hard. Number 2 is that you see how difficult it was to figure out which one was the winner. So you're going to apply the same problem here. You've got more than 1 possibility. Which one of these is the winner? Again, I'm only going to put 1 here because I'm not going to screw you that bad. Which one couples to this one? Is it this one to that one or that one to that one? And you're going to go through the same process I just did right here. Right, you see how that's going to work? It's going to be exactly the same as this. It's just kind of reformatted in a different way. I just like this because, for one, it shows me that I like this mixing it up this way, because that way you can't try to remember some formula that only fits this example. I'm going to give you a different example. Again, I cannot emphasize enough, don't just write down the cheating method. Okay, starting to run out of time, so let me remind you about Henry. What we did next is we got into solutions mixing, which then led to Henry's law, Raymond's law, and then we got to phase diagrams, which is graphical, and I did include a graphical question on the test because I didn't do that last time, and I felt pretty bad about that because graphs are easy. So remember that we really changed directions at this point and started talking about liquid mixtures. And remember what we defined first were excess functions, which were the sum of all the things thrown into the pot. This, this partial volume minus just the per molar volume, which is just the density. It's really, it's actually 1 over the density. That's a little factoid, it doesn't matter. And remember that this would be 0 for ideal, for an ideal solution, and the same for the change in U would also be 0 for ideal. And I also want to remind you that the partial volume is the change in volume per addition of, let's call it species I. We're at constant T, constant P, constant P from now on. And remember this other weird notation, just to remind you that this is a solution is all that this does. Remember that this was 18 mils per mole for water in water, but it was 18 mils per mole for water in excess ethanol. And I had to say excess ethanol because remember that that number is a function of the molar ratio, mole fraction. That's mole fraction. And so at the very far end of that graph I drew on the day I covered that, 14 was water at infinite, but technically infinite dilution because it was at the end of the graph, infinite dilution in ethanol. So anyway, ideals have this, and that's why delta mix H is 0 joules, again for ideal. Sounds like true and false type questions. What that does is, that means I've only got an entropic contribution to delta mix G. And I'm going to actually switch this to per mole. And remember I told you I'm going to just be very careful about making sure if you get confused per mole or not per mole that it's not going to matter. Because I get confused. Remember that there's 2 terms here because there's 2 things present. That's technically extensivity. And remember that this automatically means that the entropy is minus R chi A ln chi A. And these formulas, by the way, are on the cheat sheet, but you got to know what to deal with them. And again, don't worry, I per mole, not per mole. I'm not going to make that. I will make sure that questions are devoid of having to know that. And this comes about because for the same reasons that we just talked about reactions. That's why we're talking about chemical reactions and this stuff. Actually, they do kind of flow into each other because what I'm doing is I'm measuring the thermochemical properties of a solution. Do the chemical potentials drop if 2 things mix? If that is true, then they mix, right? But how do I know? I know by the vapor pressures. I know by the chemical potential of the vapor. The chemical potential of the vapor is the same as the liquid. So what I can do is measure the chemical potential of the vapor, and then if they see whether there's a drop, and then I automatically know that the same is true of the liquid because they're in equilibrium. Now, that's a mouthful, isn't it? Just remember, okay, I'm stealing equations for vapors to see whether what they're doing. Because it's a chemical potential, it's automatically the same number for the liquid. And again, there's not a lot of vapor, so they don't have a lot of energy, but that's okay. I divided by the number of moles out. Okay, now again, these are still ideal. And of course, ideal means that Rayout's law is followed, which is kind of A or B, which it still always kind of bothers me. Okay, so now remembering that the chemical potential of the vapors is going to be defined by their drop in pressure. Remember that this is a little funkier than last time because our reference pressure is not 1 bar. We're going to change the reference pressure to the pure partial pressure. That's what this is, because it's massively unrealistic if you don't. Because no matter how we construct the number on the table in the back of the book, really, the vapor pressure is that of the pure liquid, right? Water, as you did on your homework, is 3,000 pascals. It's really kind of going to make a bloody mess if we choose a different reference state than the actual pure partial pressure. And also recall that this is not the mole fraction in the liquid. Sorry. This is the mole fraction in the liquid phase. It is not the mole fraction in the gas phase. If it was the mole fraction in the gas phase, this would be perfect. But our approximation, Radiant's law approximation, is to use this idea of partial pressure, but not to use the mole fraction in the vapor phase, but to use the mole fraction in the liquid phase and assume that they're the same. I would normally have said, even now, I would say that would work, I'm sure, to a huge extent, and I am hugely wrong. It almost never works. And so the first way to slap a Band-Aid on that is to use Henry's law. Henry's law, which just redefines the pure partial pressure by a number that will make it work so that I can still use this mole fraction, liquid phase mole fraction. That's kind of what you're still trying to do. You still want to write all these equations with mole fractions in them, so you just redefine the pure partial pressure so that it works. And the ultimate fix is to use activity. Okay, noting that what you really want to get to is this quantity here, which again is a perfect, insert this into your equations for chemical potential. If you know what this is, you've got all the answers perfectly. So we call that the activity. We'll call that activity of A. I'm just taking A. I'm using A because A tends to be our solute. And what we did was we still wanted to use mole fraction, and we just came up with something that's not the pure partial pressure or Henry's law, but anything that makes it work. Now, what we went from there turned into kind of a bloody mess. Now, recall that I then equated, that one day I drew all those equations on the board. There were 6 of them, and it was a little funky. I made them, in the middle. What I did was I wrote a handout, in case you didn't notice. There's lots of handouts, by the way, if you haven't been looking. And what I've done is I've used this sucker to explain Henry's law and Rayleigh's law. I basically wrote up the notes in class. It's a handout. Remember I said I've made this test kind of memorization based, so maybe you want to have that one handout. It's a decent amount of stuff, but if you have that one pat, I think you're going to be okay in terms of understanding, Henry's law, Rayleigh's law, and the ultimate boo-boo fix activity, which remember that this is technically K. If you're a solute, this is technically the pure partial pressure. If you're a solvent, is also any of the numbers in between that make it work. Okay, then last bit, I'm just going to say 1 or 2 things, and obviously I'm focusing on things that are on the test. When we've done phase diagrams, I'm kind of out of time, but I wasn't going to say too much about this anyway because we just started doing it. And okay, so I promise that this is the one with graphs. Now I asked a graph question on the homework. So a graph question based on the P versus T phase diagram. And I can kind of do this in my sleep at this point. And notice I'm drawing the water. I'm drawing a water-like one. This is the critical. This is the gas. This is the liquid. This is the solid. And okay, that's all fine and good. Remember that we can define all this with Gibbs phase formula. We've always got temperature and pressure. You can add a degree of freedom by mixing ethanol and water, but the chemical potentials have to be equal if you have more than one phase, so that's why this kind of makes sense the way it does. This is why you have lines, open spaces, and points. I've gone over that. Now remember when it came to actually building the graph with numbers, I started out with a graph and then I got an equation. Let me remind you what the graphs were. That was me drawing the chemical potential versus temperature. And again, I'm still just talking about, I'm talking about water. Let's just say it's water. And you know that the solid is present at first, but because the change in chemical potential with respect to temperature, constant pressure is minus entropy. You know that the liquid has a harder slope and the gas harder still. And so therefore, since this is temperature, this is the melting. Actually, I'm sorry, I should call that fusion. Remember, that's the IUPAC. And of course, this is the vaporization, or the boiling point right here. And you remember what happens with pressure. If we have pressure, these lines go up, and that's because the change in chemical temperature with respect to pressure at constant temperature is volume per mole. So these go in two different directions. And remember that what I did was I drew new lines at different pressures, looked at where they cross, and that's how I could get whether these lines, like for the solid liquid, whether it's sloped left for water or sloped right for basically everything else. Okay, so that was fine and good. So remember, Gibbs phase rule grossly defined it. This gave me an idea of the general shape, but the way that I actually got equations to, to plug in numbers, which, if on the test is just a giveaway, right? That's a giveaway because all you got to do is remember to use SI units. And it just reminds you that the way we started with this was equating, oh God, I'm sorry I didn't write it. You would equate the changes in chemical potential of two phases. Remember, we just did this last time. You end up with this guy here, which is a real pain. Remember that this will be the process for fusion or vaporization or sublimation. A numerical question will give you those numbers. Delta S is always a pain, so we convert this to delta H, which is fine in our constant temperature and pressure world. And then what you can do is bring the dt over, integrate it. Now you've got equations, not just a general feeling, does it go left or right? You've now got equations that define everything perfectly as long as you're given a starting point. A numerical question on this will be, all the constants are given to you. That's a given. So if I do that, I was obviously in the first section. And yeah, well, that's about all I got. So.